Hey, this is Charlie Thompson, and this is the Chapter 7 lecture video for climate change. On the cover slide, we've got what is called the Grand Canyon of Greenland. This is actually on the ice sheet in Greenland, and this area should not be melting like this, but it is, and it's dramatic and scary. So before we get into what we're going to be talking about for real, let's just hit some of the high points and some of the general ideas. It's warm now. You can see this is a temperature record from 1880, which were some of the first years we had reliable temperature records. Up to the present, you can see that the 3 warmest years ever recorded on Earth were the last 3 years. The 11 warmest years on Earth have all been recorded in the last 11 years. So there is a clear trend of warming temperatures. And in fact, the rate has been increasing recently. So the rate of warming is increasing. So it's getting warmer faster. 2025 marked the warmest that many regions had seen compared to 1991 through 2020. As you can see, the same thing is true 23, 2024, 2025. Much of the Earth is showing the warmest conditions ever recorded for those regions. This is a map done by a group called the Conspiracy of Cartographers, and they take old gas station maps from the 50s and 60s and then superimpose sea level that we will be looking at in our future. So this is after Greenland and Iceland have melted. You can see that the Central Valley is largely an inland sea, that the Bay Area is enormous. San Francisco's mostly gone. The Central Valley, you can see the Sutter Buttes are an island. Here is a closer view of that showing the Sutter Buttes. You can see all of Sacramento, Davis, all that's, in fact, everything up to the foothills is going to be underwater. Different map. I hope you check out their stuff. Florida is going to get hit even worse than California. Much of Florida is very, very low in elevation. And the bedrock is limestone, which is porous. So it's not like you can put a seawall around the edge of the state and keep the water out. It'll just flow through the ground. So looking at this video, these are temperature anomalies, and you can see starting in 1880, most of it was blue. A few areas are yellow, but the blue indicates cooler than average temperatures. And as we go through the 30s, as we go through the 40s, the yellows are giving way to oranges, the blues are giving way to yellows. As we get into the 70s, the oranges are giving way to reds, until we get to the present, and you can see one of the few areas where the temperature is slightly cooler. It's actually because of global warming, and that's because of all of the freshwater ice water flowing off of Greenland as Greenland is melting. It's actually making the North Atlantic considerably cooler. Other trends you can see, the tropics are warming more slowly than the poles. The poles are warming 4 times as fast as the tropics, something like that. So temperatures all over the world increasing. I love this quote. Climate change will manifest as a series of disasters viewed through phones with footage that gets closer and closer to where you live until you are the one filming it. I think that's the way climate change is going to hit a lot of people. Climate change is something that they probably think of as something that's going to happen in the future and something that's happening in another place, but it's happening here and now. So some examples. This was the Greenland ice sheet a couple of years ago. This should all be white ice, but there, as you can see, there's a couple inches of meltwater on top of the ice sheet in Greenland. Huge, massive fires, wildfires across Australia, massive flooding across Australia. So one of the things I'll talk about is this idea of hydrometeorological whiplash, that we are going from drought and fire to flood. Sacramento has been having record-breaking weather. 2022 shattered the record. We had never gotten less than an inch of rain between January and mid-March. In fact, you can see the lowest you can see the lowest was 1.18 inches. So we usually get between 1 and the 10th driest, 2.3. 0.05, 5/100ths of an inch from January 1st to March 13th. The driest section we have ever recorded in Sacramento. Sacramento ended its longest dry spell with the wettest October on record. This is what I'm talking about with that hydrometeorological whiplash. This is Daniel Swain, weather researcher from UCLA, who wrote a paper on this very topic. Events globally, global events in 2023 was the warmest year on record for the globe. It was North America's warmest year, Europe's second warmest, Asia's second warmest. Hurricanes, floods, droughts in 23. 24, the warmest year ever recorded on Earth. North America had its warmest year, beating 2023. Europe had its warmest year. Asia had its second warmest year on record. 2025 was the third warmest year. So again, the three warmest years, 2022, 23, 24, unless it's 23, 24, 25. That's good, 23, 24, 25. Every decade since the 60s has gotten warmer across the United States. In fact, every decade looks like maybe even since the 40s has gotten warmer. Here we have 81 through 2010. Here we have 91 through 2010. So these are 3 decades averaged out. If we just look at individual decades, you can see that is very true from the 1960s up into the present. Every decade has been warmer than the decade before it. The 3 warmest years all occurring in the last 3 years. This record going back to 1880. And one of the things I need to talk about is what a big deal a few degrees are. So 20,000 years ago, there was half a mile of ice over this over Randall's neighborhood. Temperatures were 4.5 Celsius degrees cooler 20,000 years ago. So we're going to call that one ice age unit. One ice age unit cooler gets us into the coldest part of the last glacial period. We are going one ice age unit warmer in roughly 86 years or so. So let's see what that looks like. If we go back 20,000 years ago, last glacial maximum, there were over 6,000 feet of ice over Toronto. This is in meters, 900 meters, multiply it by 3, 2,700 feet, 3,600 feet, 10,000 feet of ice on top of Montreal. 4.5 degrees cooler is the difference for Montreal of 10,000 feet of ice and 0 feet of ice. So we are aware of the changes. The IPCC, Intergovernmental Panel on Climate Change, these are observed changes. So global temperatures, warmer. Troposphere, warmer. Lower atmosphere, warmer. Precip and humidity, more. Expansion of Hadley circulation, greater. Ocean heat content, sea level rise, ice loss, amplification of atmospheric CO2, acidification of the ocean, warming of the land, warming of the global. These are all observed changes. These are not predictions. These are things that scientists have observed. The temperature over the last 1,000 years was cooling right up to the Industrial Revolution, at which point the temperature began rising rapidly, and it's still rising. We don't know what's going to happen. This is supposed to illustrate we are here and we don't know where we're going. Will the climate be hotter? Will the climate be much hotter? Will it be 4 or 5 degrees warmer? Or will it be a degree or a degree and a half warmer? That depends on what humans do. And that's why we don't know. We don't know because we don't know what humans are going to do. Maybe humans will rapidly adopt renewables, in which case we could limit warming to 1.5, maybe 2 degrees. Otherwise, we're looking at 4 or 5 degrees of warming by 2100. 4 or 5 Celsius degrees, which is roughly 10 degrees of warming, 10 Fahrenheit degrees. So let's start the Chapter 7 concepts. How do we know about past climates? Proxy data, we'll talk about that. Why is climate change in the past? Milankovitch cycles, we'll talk about that. How do we know the climate is changing now? Because we can see it. How do scientists model climate change? With big computers. How are governments and people responding to climate change? Not well, really poorly. we'll talk about that too. So here we've got a record of temperature and CO2 for the last 800,000 years. Currently, CO2 is over 424 parts per million. When this graphic was drawn, probably 2007, CO2 was below 400 parts per million. Now it's 424. The highest it's been over the last million years was about 280. CO2 has ranged from 180 to 280, 180, 280, 180, 280, 180, 280, 180, 280, 180, 280, 180, 280, 424. So there is way more carbon dioxide in the atmosphere than when I was born. When I was born, it was closer to 300 something parts per million. So that's the temperature and CO2 record. The CO2 is the main driver of the current climate change. We'll talk about that in a bit. Here's the last 1,000 years, slightly more detailed, that the climate has been cooling for the last 1,000 years, right up to the Industrial Revolution, and then the climate began to warm across the planet. Here we've got the last 10,000 years of Earth's climate. Again, we've got a warming trend starting 6,000, 8,000 years ago, right up to the Industrial Revolution. Now we are about 1.5 degrees, 2 degrees warmer than pre-industrial levels of temperature, on our way to 4.5 or 5 degrees. So this is projected, but the blue is what we've already seen, and this blue line is continuing to rocket up. How do we know? Proxy records, tubes of stuff. Proxy record is a record that doesn't tell you about the temperature, but it tells you about something else. So pollen tells you what plants were growing. If it was pine trees and now it's oaks, it was cooler and wetter before, and now it's drier and warmer. Unless I got that backwards. Oaks, warmer and drier. Pine trees, cooler and wetter. Ice cores, looking at the chemical content of the ice, tells us about the temperature. We can also directly analyze the bubbles of gas to tell us what the atmosphere was like. We can look at ocean bottom sediments. We can look at growth rings in trees. All of these conveniently are tubes of stuff, and I'll show you some pictures so you know what I mean. This scientist is holding up a sediment core that was drilled out from the bottom of the ocean. So it comes up in a big tube, and then they cut it in half so that they can analyze it and look at it. So we've got examples of ocean sediment, ice cores. This lady's drilling out a coral reef. This is fossil pollen seen under a microscope. Pollen is extra useful because it's very durable. It's hard, so it sticks around. And you can identify what the species of plant was just by looking at the pollen. So if you're a palynologist, you'd be able to say, oh, these blue spiky things are this, and this orange basketball thing is that. So it has to be something that's deposited year after year, growth rings on trees, layers of ice, all of those things provide us with core samples. This is the Glomar Explorer. It was used to go around the world and drill through sediment and then retrieve tubes of ocean sediment that allowed scientists to date it and figure out what's going on with climate. Here's a snow pit looking at the different layers of snow deposited. Eventually down at the bottom, the weight of the snow on top will compress it to ice. And then they can take a core of that and cut it up, analyze the gas bubbles, analyze the chemical composition of oxygen to determine the temperature. So here's a video about ice cores. There's another video about Willy Dansgaard and how he discovered the relationship between temperature and oxygen isotope ratios. It is a great video. I think you have to watch it as a quiz question anyway. We're not going to watch it now. Tree ring. This scientist is taking a tree ring core from a hemlock in Lassen. That every year trees add on another layer of growth. And so by counting the rings, you know how old they are. At the end of the year, when it's wintertime, the tree grows more slowly and it puts on these layers of darker wood that we can use to date it. If the conditions are harsh, if it's dry or hot, you'll get narrow rings. If conditions are more favorable, you get wider rings. And so you can compare rings between different trees from the same area and they'll match. Like these like two narrow rings right here would have been formed at the same time. And then looking at another tree, the rings might be in a different point in the tree, but you'd be able to go, oh, this was the 1980, 1981 growth rings. And then by by using the ability to match different tree cores, you can say, oh, like, yeah, whatever. 3 bad years and 2 good years, that's 1880. Oh, and here's where it is there. So we know this is 1880, 1870, 1860, 1850. And then they can use those to match up different tree cores across Europe and across the American West. We have 2 different tree ring core records that go back 10,000 years. So not from one tree that's 10,000 years old, but matching up multiple tree rings from different trees in a region, we can assemble a long-term climate record. Looking at living trees, looking at dead trees, looking at trees used in buildings, they can date those trees. And by looking at the width of the rings, they can tell what those years were like. Another video on tree ring dating. Looking at pollen from pack rat middens. This is a pack rat midden in the Grand Canyon. So this is urine. Pack rats will nest in the same nest for many generations over hundreds of years. And they have this habit of pissing on their nest. And it traps and collects pollen. You can wash out the urine and collect the pollen and look at it under a microscope, and you'd know what plants were growing when that pack rat was peeing on the nest at that time. Another midden. There is, in fact, there's a whole internship program. If you want to go to the Grand Canyon and do pack rat midden pollen analysis, you can do that. Contact me for more data. So looking at Earth's climates, looking at the last 70 million years, it was warmer. The climate has been cooling. One of the really cool theories is that the Himalayas, the uplift of the Himalayas, revealed a lot of limestone that when it got rained on, absorbed carbon dioxide and pulled so much carbon dioxide out of the atmosphere that it got colder. That's a great hypothesis. 56 million years ago, there was this sudden jump in temperatures. We're not sure why. Might have been melting methane hydrates. But the warming was very rapid. Caused sea levels. Sea levels at the time were 22 meters higher, so 66 feet higher. The temps were 5 to 8 degrees warmer. CO2 levels rose 600 to 800 parts per million. Right now they are 424 parts per million. But they're increasing. And so one of the concerns is that temperatures rose more slowly during this increase in temperature, which resulted in mass extinctions. So much warmer temperatures, much higher sea level, mass extinctions, and all of that was from a slower increase than today's increase in temperature. So this is kind of what the Bay Area would have looked like during that time, during the PETM, that thermal maximum period. The last 5 million years have seen the rise of human civilizations, and we've been in most of that time, for the last 2.5 million years, we have been in an ice age. Ice ages last for hundreds of millions of years, and they're made up of these glacial periods, 90,000 years of cold, that's a glacial period, and then you have a 10,000 year warm period called an interglacial. We are in an interglacial that began 10 to 20,000 years ago. So we should be coming out of the warm period, going back into a cooling period. And that's, in fact, what all those temperature plots showed, that from 6,000 years ago up until 1850, Earth had been cooling, as we should be entering a glacial period. But we're not, because of CO2, mostly. Over the last 5 million years ago, let's look at the plot. So a couple big changes, huge, 14 degrees warmer, 28, so 30 degrees warmer. That's a really big deal. And here we've got that jump, the PETM, that thermal maximum, when it jumped up it was 5 to 8 degrees warmer than present. But then after that, we see this cooling trend. Cooling, right up until the Industrial Revolution. Some other fun things, huge shifts in temperature, including maybe snowball Earth, the end of the dinosaurs, 65 million years ago, right in here. For the last 2.5 million years, we've been in the Pleistocene, with this series of 100,000 year cycles, 90,000 cold, 10,000 warm, 90,000 cold, 10,000 warm, 90,000 cold, 10,000 warm, right up until the Industrial Revolution. So showing the same thing, we are here. Here we've got hothouse Earth, coolhouse Earth, and now we've got since the Pleistocene, we've been in this ice age. During this period, actually before that, my bad. During this period, during the hundreds of millions of years ago, 500, 600, 700 million years ago, we had repeated snowball Earth events when the Earth got colder. So there was more snow and ice, so it got colder, so there was more snow and ice. And eventually Earth pretty much froze over, except for maybe some open water at the equator. As Earth was frozen, it was reflecting most of the light coming in, so it was very cold. But because it was all ice, and there were still volcanoes erupting with CO2. The CO2 built up until the Earth got warm enough to start melting the ice, and then we had another positive feedback loop. So there was a positive feedback loop as Earth got colder. As it got colder, there was more snow, made it colder, more snow. But then once there was enough CO2 to start it melting, as it melted, it exposed dark land, which warmed the Earth, which melted the snow, more dark land, higher temperature, melt the ice, more dark land, melt the ice, more dark land. So here we had big, we don't know a whole lot because it's hard to find rocks from this time. As we get closer to the present, we know more and more and more. Here we've got that general cooling trend. Here we've got the last million years. We've had this cycle going on for the last million years. And then we get right up into the present and temperatures are bumping back up. So again, the last 800,000 years, we've now drilled down and found older ice, but it hasn't been analyzed. We're going to push this back to 1 million years to see what was going on 1 million years ago. But current levels of CO2 are 424, when the highest it's been in the last 100,000 years or the last million years. The highest CO2 has been is closer to 300 or 280 parts per million, between 180 and 280. 180, 280, 180, 280, 424. Again, over the last 1,000 years, cooling trend, industrial revolution, CO2, increased temperatures. If we look at the last 20,000 years, there's a couple things that have happened. Our last ice age began 2.5 million years ago. So the current 20,000 years are still in the Pleistocene or the Holocene, the most recent period. So the last glacial period lasted from 110,000 years ago to 10 or 20,000 years ago, depending on where you were in the world. And we've been warming. There was this abrupt drop in temperatures, the Younger Dryas, 12,000 years ago, 15,000 years ago, and then things returned to normal. 800 to 1,200 years ago, things were slightly warmer. You can't really see it on this. The medieval climate anomaly. So here we had the cooling dip. We're not really sure why it cooled, but then things returned to warmer. There was a brief blip of warmer temperatures in the North Atlantic that allowed the Vikings to expand, and then things returned to colder conditions. But there wasn't a global warming 800 to 1,200 years ago, or from 800 to 1,200. There was not a global warming. It was just a local blip of warming. Since then, temperatures have been cooling right up until the Industrial Revolution. Things have been warming since the Industrial Revolution. Why did climate change in the past? People weren't burning fossil fuels, so why did it burn? Why did the temperature change, rather? And the answer is Milankovitch cycles. Milutin Milankovitch was a Serbian mathematician who said, hey, I think there's these 3 different cycles. And if we look at them, I think they come together and make it colder, and they come together and make it warmer. So we've got orbit changes in the shape of the orbit on a cycle of 100,000 years. We've got where Earth's axis is pointing at. That changes on a cycle of 26,000 years. And then the tilt of Earth changes from 21.5 to 24.5 degrees on a 41,000 year cycle. So let's take a look. We've got changes in the shape of the orbit on a 100,000 year cycle. Earth's axis right now is pointing at the North Star. And right now we are farthest away in Northern Hemisphere summer, so our summers are a little cooler, and we are closest in Northern Hemisphere winter. So right now, Earth's wobble, the wobble of the axis, is creating less seasonality. We are closest in the winter, we are farthest in the summer. But in 13,000 years, Earth's axis is going to be pointing in a different direction. So we will be closest in the summer and hotter, and we'll be farther away in the winter and colder. So Milankovitch put these three things together and said, yeah, we've got this cycle of roughly 100,000 years. Roughly 100,000 years of 90,000 years of cold temperatures, and then a brief 10,000 year warm spell, and then back into cold, and then 10,000 years of warm. So we've got changes in the eccentricity or the ellipticality of Earth. It goes from being more circular to being more oval. That's one of them. So a second one, axial precession. The wobble. So right now we're closest when the northern hemisphere is pointing towards the sun, and we're farthest when we're pointing away from the sun. And in 13,000 years, let's see if I can stop it. No. Yeah, in 13,000 years, we will be closest in summer and farthest in winter, as opposed to right now. We are farthest in northern hemisphere summer. So this is showing northern hemisphere summer because the North Pole is tilted towards the sun. So we are farthest in the summer and we are closest in the winter. But in 13,000 years, we will be farthest away in the winter and closest in the summer. So another one, changes in Earth's tilt, going back and forth. So on a cycle of 41,000 years, we get more seasonality and less seasonality. And then it's interesting, over the last 41,000 years, from 2.5 million years ago to 1 million years ago, from 2.5 million to 1 million years ago, the tilt cycle was most important in driving Milankovitch cycles. And a million years ago, that shifted to the ellipticality being more important. Scientists are still studying this, but I think it's really interesting that we're still studying these basic science of how Earth works. Sunspots, mechanisms of natural climate change. So the reason that we have these glacial and interglacial periods is the Milankovitch cycles. There are other natural changes that take place, and some of them affect the climate and some of them don't affect the climate, but scientists have looked at all of them. So, for example, sunspot activity. If there's more sunspots, the sun is more active and is putting out more energy. And so looking at, for example, the Maunder minimum, there was a period of greatly reduced sunspot activity, but as you can see, didn't really have a huge effect on temperatures. And now we have been in a period of reduced activity at the same time that temperatures are spiking. So sunspot activity not directly correlated with temperature, the same way concentrations of greenhouse gases is. When sea level was lower, there was more land exposed. This wasn't necessarily a cause of climate change, but it was an effect of climate change. So you could walk all the way from Australia to Papua New Guinea. You could walk from Indonesia to Thailand. You could walk from France to England. You could walk from Cuba to Florida. All of that was dry land. And one of the consequences is that there was people living in what is today the ocean in this region called Doggerland. 16,000 years ago, all of this was dry land. And as the huge ice sheets melted, this was underwater by 8,000 years ago. And then by 7,000 years ago, just the dark green areas were sticking above the ocean. Plate tectonics plays a role in climate change. I already mentioned that the impact of India and the uplift of the Himalayas contributed to carbon dioxide being absorbed by the limestone weathering away. But something else is just the orientation and position of the continents. The bigger the continent, the more continentality. And so we had huge continents at high latitude. So there were enormous deserts because that inland effect, way more inland with a way bigger continent, and then also more effects at the high latitudes because of greater continentality combined with high latitude. So it's something I had never thought of. Oh, right, when the continents were all together, there would have been more continentality. Speaking of plate tectonics, the closing of the Panama Land Bridge. So there used to be an equatorial warm current that went all the way around the equator. It would just keep going around and around and around the equator. But then after 20 million years, or more recently than 20 million years, when we had the Panama Land Bridge, that created the Gulf Stream. The warm current coming across the equator ran into the land here and got diverted towards the poles as the Gulf Stream. So you can't have the Gulf Stream before you have the Panama Land Bridge, which is, I think, interesting. Volcanic eruptions usually drop temperatures. They put aerosols, the ash, into the atmosphere. They do emit some carbon dioxide, but they have a net cooling effect. Here we've got Mount Pinatubo in 1990. We've got these 4 well-documented examples of drops in global temperatures for a year or two after a big volcanic eruption. We've had some big eruptions 760,000 years ago. All of this was covered with ash from an eruption in California. Parts of California were covered with 600 feet of glowing ash. Although it was 760,000 years ago, so there weren't people here. Right. Let's talk about feedback. Feedback is when the behavior of a system, or when the output of a system affects the behavior of the system. So if the output increases the behavior, that's positive feedback and it destabilizes the system. If the output reduces the behavior, we say that's a negative feedback and that stabilizes the system. So we've got a couple feedback loops. We've got ice albedo, water vapor, ice elevation. These are all positive feedback loops. All the feedback loops that we're going to talk about are positive feedback loops. So ice albedo, ice melts, exposes dark land, absorbs heat, warms, melts the ice. That continues. Also, as Earth warms, there's more forest and wildfires, and that ash gets deposited on the ice and darkens it and makes it melt more quickly, which warms the temperatures, which melts the ice. So the dark ash, there's a video that I put in the playlist from Black and Bloom studying how black carbon and algae are increasing the melting of the ice sheets. So here we've got white reflective ice and darker more absorbing water. So as the ice melts, you get more water. The water absorbs the heat. As the ice melts, you get water. But not all the ice, well, we'll get to that. So snow and ice melts, dark surfaces revealed, increases temperature, snow melts, dark surfaces, increases temperature, snow and ice melts. This is Greenland. This is not a lava field in Hawaii. This is the Greenland ice sheet showing just how black and dark it is. Another shot of the Greenland ice sheet showing how dark it is. Another shot of the Greenland ice sheet. So it's not all white and reflective like it used to be. And forest fires are part of the reason that this is increasing. Also, and I forgot to mention this, increased shipping traffic in the Arctic, burning the equivalent of diesel fuel. So as there's less ice, there's more ships. As there's more ships, there's more exhaust. As there's more exhaust, there's less ice. As there's less ice, there's more ships. Less ice, more ships. Less ice, more ships. And as these systems change, they hit tipping points. A kayak is a good example of a tipping point that you can lean over in a kayak, and if you stop leaning, you'll bounce back upright. If you lean a little bit more, you'll bounce back upright. But at a certain point, if you lean over too far, the kayak will flip over from one steady state into another steady state. So a kayak is a good example because once you lean too far, it flips over and will become a new steady state that won't change. It's resistant to change now. Another important idea is once the threshold is crossed, the system will keep moving. Like a semi-truck heading for the edge of a cliff. Well, you can take your foot off the gas, but that's not going to slow the truck down, and it's still going to go off the cliff. Tipping points and systems are connected. Let's look at some examples. Yeah, there's one article or one video about tipping points, another PBS video about the effect of tipping points. Let's look at water vapor. As the planet warms, there's more evaporation, so there's more water vapor in the atmosphere. The water vapor absorbs heat, warming the planet, so there's more evaporation, so there's more water vapor, which warms the atmosphere. Every 1 Celsius degree increases the water vapor capacity by 7%. So if right now we've got a planet that's got at least 10% more water vapor. So the storms are 10% stronger. The flooding is going to be 10% stronger. The heavy precipitation events are going to result in 10% more precip. More water vapor, more warming. This is Stefan Rahmstorf. This is a video that you're going to have to watch to answer some quiz questions about. He's talking about tipping points in the Arctic, including the ice elevation tipping point. So because the ice sheet in Greenland is so high, it's cold. It's cool to be high. But as the ice melts, the elevation at the top of the ice sheet is at a lower elevation. And because it's at a lower elevation, the air around it is warmer, so it melts more rapidly. And now the air around it is warmer, so it melts more rapidly. So there's a chance that we have already hit the tipping point with the Greenland ice sheet, that it will just keep melting for the next several thousand years until there's nothing left, because it is now in air that is too warm to keep it being ice. Thank you, Stefan. Let's talk about the carbon budget, which on one hand is super important, but on the other hand, it's not super exciting. So the most important part are the key words. Carbon comes from sources, it is stored in sinks, and it moves in flux. So the carbon that is stored is in a sink. The carbon that is emitted, like when we breathe, we emit carbon dioxide, so we are acting as a CO2 source. Plants absorb CO2, so they're a sink. And then the carbon going from you to the plant, that's the carbon in flux. So sinks are the reservoirs where it's stored, like the atmosphere, the oceans, the soil, plants. Flux is carbon moving back and forth. And the amount of carbon that's moving is a very small fraction of the total carbon. So there's an enormous amount of carbon in Earth's carbon budget, but the amount of carbon that's actually moving is relatively small. And until humans started belching out so much CO2, the sinks and sources were balanced. And now we are emitting more CO2 than is being absorbed by these sinks. Fossil fuels is the biggest reason. Clearing forests, decreasing the parts of the system that absorb CO2 is another part of it, but really burning fossil fuels is the biggest. The oceans are absorbing much of the CO2 and much of the heat, which is good, except that it makes the ocean more acidic, which messes up the shellfish like clams and oysters that take calcium out of the ocean and make it into shells. In fact, the the Point Reyes Oyster Company, the Hog Island Oyster Company, that's who they are. The Hog Island Oyster Company is growing oysters up in Humboldt Bay, and they are already having to acidify the water to keep the shells of the little baby oysters from dissolving. CO2 has also acted to make plants grow more quickly, enhanced photosynthesis. We can't compare tree rings pre-1950 and post-1950 because trees after 1950 have been growing more rapidly. So we can compare them to each other, but you couldn't compare a tree ring from 1950 to pre-1950 and expect that the conditions would have been the same. They're not. More CO2, plants grow more quickly. So this is a diagram of Earth's carbon budget. The numbers in white represent the gigatons or billion tons of carbon in sinks. The yellow is carbon in being released. So that's carbon sources. So 120 gigatons of carbon absorbed by plants. So that's absorbed by plants, but then plants are emitting 60 and decomposition releasing another 60. So 123 being taken up and 120 being released every year. The numbers in red are from humans. Humans are emitting 10 to 20 gigatons every year. So not a whole lot, especially compared with like the 40,000 gigatons of carbon in deep ocean water, 6,000 gigatons in sediments, 10,000 gigatons in fossil fuels, in fossil carbon. So humans are emitting a relatively small amount, but it's enough to throw the system out of balance. It's driving increased photosynthesis on land and in the ocean. Yeah, that's good. The Keeling curve is carbon dioxide in the atmosphere. It's named after Charles Keeling, who taught at Scripps. He started analyzing carbon dioxide on his honeymoon back in 1959. This is the longest record of carbon dioxide in the atmosphere. And the current presidential administration has cut funding to monitor CO2. Because if you stop looking at CO2, you can't say the climate's changing. Well, everybody will, but I think that's what they're thinking. If we look across the world at evidence for climate change, it's not hard to find. Ice is melting in glaciers. Ice is melting in the ocean. The ocean is warmer. Sea levels are higher. There is more heat stored in the ocean. Temperatures over the land and the ocean are higher. Temperatures over the land are higher. There is reduced snow cover. There is more water vapor. By every objective standard, the climate is changing in a bad way because of humans. Yeah, rising temperatures, melting ice, rising sea levels, increased water vapor, all of these are things that we have seen. This is all observed. Temperatures getting warmer. 2025 was the third warmest year on record. 2024 was the warmest year on record. If we look at temperatures since 1976, 1976 was the last time we had a year that was below average. Every year after 1976 has been warmer than average. So if you were born after 1976, you have never spent a year on Earth when the temperature was at or below average. Every year has been above average. Looking at it by decades, the 60s, the average temperature of the 60s, the 70s were warmer than the 60s, the 80s were warmer than the 70s, the 90s were warmer, the 2000s were warmer, the 2010s were warmer, and the 2020s will be the warmest decade ever recorded on Earth. So every decade since the 1960s has been warmer than the decade before it. Looking at temperatures again from 1880 to the present, we can see every decade has been warmer than the decade before it. We can also see the effects of Mount Pinatubo. Looking at ice melting on sea and the land. Looking at glaciers, they are losing ice globally. So looking at both Greenland and Antarctica, they are both losing ice. Greenland right now is losing ice at a faster rate than Greenland. Greenland is losing ice at a faster rate than Antarctica. Greenland is losing 269 billion tons of ice every single year, as opposed to Antarctica losing only 142 billion tons of ice a year. But again, the trends are obvious. The trends are not really stopping. And so we are seeing continued loss of ice from Antarctica and Greenland. You can see the area of ice loss on Greenland is expanding every year to higher and higher and higher elevations. Yeah, not good. If we look at, Antarctica and Greenland, you can see there's a very clear melting trend in Greenland and in Antarctica. And one of the issues in Antarctica is that the white stuff is ice on land. These are ice shelves floating in the ocean, and these ice shelves are breaking up. And when the ice shelves break up, the ice on the land flows more rapidly into the ocean. And so these floating ice shelves act like a cork in the bottle, keeping the contents in the bottle, but the corks are breaking up. They recently sent a remotely operated device down below the ice shelf to see what's going on, and they realized that under the ice shelf, there are new warm currents. So the air is melting the ice from above, and these warm currents are melting the ice from below. And one of the issues is some of these ice sheets on the inland portion, the ground gets lower as you go inland. And so once this contact starts melting, it's going to melt more and more rapidly until the grounded ice sheet then is broken up and floating. Included in the notes, if you go and look at the note slides, they're also in the YouTube playlist. I've included some videos. This one's on how they measure glacier melt in Iceland. This one's on how they measure ice melt in Greenland. There's Jason Bach's famous glaciologist. Thanks, Jason. This is another video on how they are measuring the effects of dark material on the snow, increasing the melting. Yeah, so variety of measurements. We are looking at melting ice in the ocean, on the land, in the soil, and that's called permafrost. So as this permafrost melts, sometimes forests fall over. Those are called drunken forests. And the reason they fall over is because they were supported by the ground that was frozen solid. And then when it thaws out, it becomes muddy and the trees fall over. And as the ground thaws, the dead material gets decomposed and converted to methane, which is a very, very powerful greenhouse gas. And so all across the Arctic, all of this melting permafrost is releasing hundreds and thousands of tons of carbon, greatly accelerating global warming. So here's a video about this lady, Dr. Katie Walter Anthony at the University of Fairbanks has been studying the rates of methane coming out of these lakes. You can actually light the lakes on fire. That's not something you should be able to do. Yeah. Permafrost causing problems with forests, causing problems with houses, foundations cracking when the permafrost thaws. Lakes are draining out as the permafrost thaws. It's creating problems all across the Arctic. All across Canada, there is enormous amounts of carbon stored in the frozen soil, and then when the soil melts, the carbon is released. As it's released and as it thaws, you might say, well, but plants are living there, so they're absorbing carbon dioxide. Right, the plants absorbed 1 billion tons, but the thawing permafrost released 1.7 billion tons. So the net is still a CO2 release as this permafrost thaws. Sea levels are rising as the ice on the land melts. So I think the best estimate is 6 feet of sea level rise by 2100 from a variety of studies. And it's affecting Pacific Island nations in a huge way. This is, I think it's Tuvalu, and this is just at high tide. This is the ocean. This is the main road around the island at high tide. Another shot from the South Pacific showing what it looks like just normally. There's your house. There's the ocean. We're looking at 6 feet of sea level rise by 2100. So there's no way these people are going to be able to live here. I believe this is on Kiribati, people wading through a flooded street after a tropical storm. So if you had crops, they're all dead because they got watered with salt water. Whatever fresh water was in the ground has now been contaminated with salt water. In fact, the nation of Tuvalu, an entire nation, an entire country, is having to negotiate with Australia to move everybody in the country away from their ancestral homes to Australia because their nation will be underwater shortly. Increased water vapor means stronger storms. This is Hurricane Patricia. She had sustained winds of 200 miles an hour and was related to the record high sea surface temperatures. Same thing with Hurricane Helene and Milton a couple of years ago across Appalachia. Record rainfall tied to record high sea surface temperatures. So those were both hurricanes. Stronger hurricanes, wetter hurricanes, stronger flooding, stronger storms because there's more water vapor being released. Stronger tornadoes. Here we've got a change in heavy precip events. Here we've got a change in hurricane energy released, and all of them are going up. Also, heat waves, droughts, precip, floods, all of these things are becoming more common, but, and I think this is super interesting, psychologists tell us that after 6 years of extreme events, they just become normal. So it's kind of like that you've heard that you can put a frog in water, and if you increase the water slowly, they don't jump out. That's not true. That experiment was done to prove the value of a lobotomy. So if you take a scalpel and you sever the connections in a frog's brain, it won't jump out of water. But after 6 years of extreme events, it just becomes normal. And we're all, oh yeah, we've always had a foot of flooding every time it rains. When, 6 years before, that wasn't the norm. But humans are really adaptable. And after 6 years, we just go, oh, I guess that's what the norm is. That's just the way things go. So I was looking for evidence or good videos, good images for flooding and wildfires, and I just got overwhelmed and I realized, oh, that's probably just as impactful to go, look, I couldn't find one video because there's a million. How cities prepare for flooding. Heavy rain floods bring renewed calls for something. High tidal surges bring floods. How can we prevent urban flooding? The deadly 1862 flood in Sacramento. Another city is drowning. Kentucky flooding. St. Louis flooding. So it's not just one place, it's everywhere. The planet has warmed, except for that blue blob in the middle of the Atlantic caused by the ice water melting in Greenland. What's causing it? What's causing the present climate change? It's greenhouse gases. It's mainly carbon dioxide, followed by methane, nitrous oxide, CFCs, and water vapor. Carbon dioxide up. A lot of carbon dioxide produced in making cement. So many researchers are looking at low CO2 methods of manufacturing cement. Methane from natural gas, petroleum, and agriculture also has skyrocketed recently. Nitrous oxide, mainly from synthetic fertilizers, also skyrocketing. Chlorofluorocarbons have decreased. Well, most of them have decreased because humans realized that they were destroying the ozone layer and warming the planet. So we shifted from CFC12 and 11 to things like HCFC22 that should have a lower amount of ozone depletion and a lower amount of global warming. But still, the world came together and made some changes in a good way, which gives me hope for global warming in general. Tons of oil burned per person. We're doing good. Australia's doing good. Saudi Arabia doing really good. Burning lots of oil, making the planet nice and hot. So the things that change the climate and make it warmer or colder, we call those forcings. And if it makes it warmer, that's a positive forcing. If it makes it colder, that's a negative forcing. And looking at all these different forcing factors, we can figure out what's going on with the climate. So here's one way of looking at it. Looking at relative amounts. So here's the amount of warming from carbon dioxide, the warming from methane, the warming from CFCs and nitrous oxide. So most of the warming is from carbon dioxide. Looking at it a different way, this is the diagram out of the textbook. You can look at natural changes, so air pollution and changes at the top of the atmosphere. I'm sorry, air pollution is not on this one. Those are natural changes, top of the atmosphere insulation, slightly more insulation, adding 0.05 watts, but greenhouse gases are adding 2.8 watts. Changes due to, at the surface, albedo of black carbon is warming the planet. Surface albedo from land use changes, like making cities or making farms slightly cooler. This is my favorite way of looking at it. So here we've got forcings expressed in watts per square meter of land. CO2 is the main driver, followed by other greenhouse gases. Some things have made it cooler, like air pollution. Aerosols in the atmosphere. Air pollution has actually made it cooler by almost a half watt. Contrails have made it warmer. Greenhouse gases have made it warmer. If you add up the things that made it warmer and the things that made it colder, the current warming is about 2.4 watts. So every day we are adding 2.4 watts of heat per square meter all over the planet every day. And the bulk, the vast majority, is carbon dioxide. So global surface temperature is actually not 0.8. They're up to 1.5 degrees warmer since 1880. We are currently in a low output state with the sun, but we're still getting warmer. So once the sun kicks back over to a high output, things should get aggressively warmer. Volcanoes make things cooler. El Nino makes it warmer. We are about to go into some sort of El Nino. It'll be interesting to see what that is like. But the dominant factor is human changes. So let's look at the climate models. So looking at computer models, so these are changes just in insolation from the sun. This is changes to temperature just because of volcanic activity, El Nino, and greenhouse gases. So if you put all those four blue lines together, you get this red line. The red line is what the climate models say should have happened. The black line is what really happened. And the bad news for us is they pretty much agree. Once you include all of the natural and human factors together, there's really good agreement between what the models say and what actually happened. So these models, they're all computer models. They're originally on weather forecasting models. It's a mathematical representation of all of the different factors that make up the climate system. So they divide the Earth up into a grid, and as computers have gotten more powerful, the grid squares have gotten smaller. They're grid across the surface and then extending up through the atmosphere and then down through the ocean. And then they set the initial conditions to a known date. So you could do it, let's set the world up as it was January 1st, 1960. And then we'll let the model run forward to the present, and we'll see how good a job it does at recreating what actually happened, because we know what happened. So you can start the model off in the past and let it run. In fact, the BBC did hundreds of thousands of runs of this. You could download a program, and it would run on your computer when you weren't doing anything with your computer. And it would just crunch away these climate models. And so then they could compare the results of the models with reality, save the best ones, make tweaks, and then run those. And then save the best and make tweaks and run those. And take the best, make tweaks, run those. And they repeated that over and over and over again. And so now the climate models are very accurate. The precision is very high. It's just that the news that they have is really bad news. None of the news is good about the climate models. Here's a supercomputer. That was impressive. Once upon a time, I was just reading an article that said that the supercomputer, the Cray supercomputer from the 1980s, is roughly 100,000. Well, an iPhone 17 is 100,000 times faster than a 1980s vintage supercomputer. I don't know what that means. It's just interesting. So forcing, again, forcings are factors that make it warmer or colder. Positive forcings make it warmer. Negative forcings make it colder. So you set the initial conditions, and then you see what the outcome is with these models. And looking at the climate models that did not include anthropogenic factors, after 1960, they diverge. Like, okay, decent, but then right here, it got hotter, but it shouldn't have. Until you put in the natural and human factors, and then we get really good agreement between the climate models. They don't predict temperatures, exact temperatures. They just predict degrees of warming or cooling expressed in watts per square meter. So like the SSP 2 to 4.5 represents 2 to 4.5 watts of warming. So like right now, we are warming, RCP 2.6 would be 2.6 watts of warming, which is pretty close to where we are at just over 2.4 watts. So this line is what we think will happen to the climate if we can keep the warming to 2.6 watts. Maybe the temperature won't get much more than 1 degree, although we've already hit 1.5 degrees. So we are still over here. So we are at 1.5 degrees. So we are hotter than even the most pessimistic models. This RCP 8.5, that's 8.5 watts of warming. That was the business as usual. So we keep burning fossil fuels like we are. In fact, the current warming has outpaced this 8.5 watts of warming. And that's going to get us to someplace around 8 degrees. So for your test questions, whenever you're asked, what do you think temperatures will be by 2100? Let's go with 8 Fahrenheit degrees warmer. Oh, what does that look like? Hey, it's a callback to the very beginning of this lecture video in which I said, well, 4.5 degrees cooler, you get a mile of ice over Chicago. But we're going 4.5 degrees warmer from 4.5 degrees warmer. Again, looking at probably 8 degrees, the 8.5 watts of warming is the business as usual. We could dramatically limit warming to 1.5 degrees or 2 degrees if we implemented radical steps to shift to electrify everything. We could totally pay for that with health savings. So many people die of lung problems and respiratory problems because of burning fossil fuels, 10 million people a year die just because they're inhaling air that was polluted by burning fossil fuels. So just in the US, we could totally pay to electrify all of our household appliances and all of our vehicles. We could totally pay for that and save money by converting to electric. And we'd have a cooler planet. But we're not. In fact, the current policy right now is to stop building renewable farms and to aggressively pursue fossil fuels across the United States. And this is going to be a big deal. So, right, most of you were probably born, I'm going to say 2000, 2010, someplace in there, probably. So when you are older, the future at this point is discretionary, and it can be a degree or two warmer, or it can be 4 degrees warmer based on the changes that we make now. And that's what this diagram is trying to show. Yeah, so just two options, 2.6 watts versus 8.5 watts. You're looking at an Arctic that is 20 degrees warmer in some places, as opposed to an Arctic that is 2 to 5 degrees warmer, as a result of carbon dioxide and changes that we could make right now. So 4.5 degrees cooler, we had 30% of Earth covered with ice sheets. When we were at the height of the last glacial maximum, sea levels were 120 meters lower, 360 feet lower. Florida was huge. The Gulf Coast was huge. There was a mile of ice over Chicago. There were 10,000 feet of ice, 2 miles over Montreal. You could walk all the way. You could walk all the way from San Francisco to the Farallon Islands without ever getting your feet wet. You could walk from Sacramento to the Farallones. There was no bay. It was all dry land. 2 meters of sea level rise gets us to exciting new water recreation opportunities in the Central Valley. If Greenland melts, we're looking at 7 meters. At that point, I will have to commute to work by kayak. 24 meters, I believe that's if we lose Antarctica. Then I gotta move because everything in Davis is underwater. And if we lose them both, you're looking at a giant inland sea where the Sacramento Valley and San Joaquin Valleys used to be. The Sutter Buttes are an island. The Montezuma Hills might be an island, but the Bay Area is huge, and all of Sacramento is underwater. This is the business as usual in maybe 2,000 or 3,000 years, but this is also what Earth looked like last time there was this much carbon dioxide in the atmosphere. Florida is going to have huge problems. New Orleans is going to have huge problems because the East Coast is flat. So as sea level comes up a little bit, the ocean runs in a whole lot. Again, back to 6 feet of sea level rise by 2100. I think that's pretty much baked in at this point. This was New York during Hurricane Sandy, which I want to say was 2008. So sea level was lower. This is the ocean flooding a coastal walkway. New York freaked out and has spent $1 billion to stormproof their subways, for example. And I remember when I heard that, I thought, oh my God, I hadn't even thought of the fact that all their subways are below ground. And if the ocean is now at ground level, it's going to flood the subways and then they're all unusable. Yeah, so $1 billion might be cheap compared to losing your subway system forever in New York. I also included a bunch more videos. This one's on how Miami's real estate market is going to collapse after sea level rise continues and they have their first big storm. That's a good one. Another video on Florida sea level rise. You can see the flooding there in the background. Another Key Largo. This is just the ocean. This is just, and they don't, because of the Republican governor of Florida, they are unable to use the words climate change in talking about this. So instead of saying this is sea level rise from climate change, they call this clear sky flooding or nuisance flooding. And one of the things that they don't talk about a whole lot is that seawater gets into concrete. The concrete will absorb the seawater, and then the seawater will actually crumble the concrete from inside. The concrete and the rebar will start rusting, and so you have the problem of concrete falling apart as a result of exposure to seawater in Florida. That's affecting parking garages and buildings. We got Key Largo. In the Chesapeake Bay, there's this entire island, Tangier Island, that is slowly sinking. They're walking down the middle of the island. This is the ocean. This is just high tide. This isn't storm surge or anything dramatic. This is just another day on Tangier Island. And the people on Tangier Island are all convinced that the climate is not getting warmer and that the ocean is not rising as they watch their houses flood. I don't know how they live. Huntington Beach, this is not just an East Coast thing. Coastal communities, especially in Southern California, are having to think about how they want to deal with rising sea level. Highway 37 on the way to Petaluma is a great example of something. They're going to spend billions and billions and billions and billions of dollars because Highway 37 is right about sea level. And if we're looking at 6 feet of sea level rise, there's going to be no way to get across Highway 37 at anything except the lowest of all low tides. So they're looking at spending billions of dollars just to fix Highway 37. Huntington Beach. Climate forecasts. So the Intergovernmental Panel on Climate Change has put out a series of 6 reports, and they've all said the same thing. All 6 reports have said the same thing. Over decades and decades, humans are changing the planet, and it's going to be bad. The only thing that's improved with time is the accuracy and precision of their warnings, which have been pretty much universally ignored, at least in the United States. But yeah, IPCC says cold days and nights will be warmer. Hot days and nights will be warmer. Permafrost will decline. The ocean will get acidic. Glaciation will not happen. Global mean sea level will rise and continue. Okay. There will be less river runoff because there will be more evaporation. So the water cycle will actually change. In addition to it running faster, there will be more places suffering from water deficits because it will just be too dry. The IPCC won a Nobel Prize for their scientific efforts to study climate change. They've put out these reports. A study looking at reports found that almost 14,000 reports said, yeah, the climate is changing because of humans. It's going to be bad. 24 out of 14,000 said, no, it's not. One of them actually I read, and it started with, given that the Russian economy is based on oil, the climate can't be warming because that would cut into our oil profits. So I think we could ignore that article. But all of those 24 articles, when the studies were redone, were wrong. New paper finds common errors among the 3% that reject the consensus. How did they do that? Well, cherry picking is when you only use the data that you want, and if it doesn't agree with what you believe, you just ignore it. Blah, blah, blah. Totally fascinating thing is all of the global warming consensus papers agree. The planet is warming, mainly because of fossil fuels, mainly because of humans. The anti-global warming papers don't agree. They all have different ideas. Some blame it on the sun, others on orbital cycles of other planets, others on ocean cycles. So all the people who are saying all of the people who are saying climate change, they each have their own reason why they say the climate isn't changing. But every one of those papers had an error in assumptions, in the methods, in the analysis that when corrected, brought the results into line with the scientific consensus. So the actual scientists are all in agreement. The only people that aren't in agreement are people that are probably getting paid by the fossil fuel industry. Sometimes when it's cold, people think it isn't warm. Again, the climate is indeed warming. Informed evidence. Yeah, everything we've talked about, everything that I'll put online for the materials that you can download, the summaries by the IPCC. Take a look through. Find which part you're going to disagree with. Is it getting warmer? Yeah. Is there more CO2? Yeah. Do we know how much heat CO2 absorbs per molecule? Yeah. Do the results match? comparing the amount of heat that we should have gained as a result of the gain in CO2, yeah, it all matches. So if you're going to say it's not CO2, you're going to have to provide another source for the warming, which nobody can, and you're going to have to show why the CO2 is not absorbing heat, which nobody can. So the consensus is it's CO2. That's pretty much it. Unfortunately, this is cutting into the profits of the most profitable industry ever, and they're not going down without a fight. Some people are saying, well, it's too late. There's nothing we can do, so we'll have to use geoengineering, which I'll talk about in a second, but there's easier things we could do. Organic agriculture would eliminate those nitrogens, would eliminate synthetic fertilizer, would decrease the amount of warming of the planet. We would have better food. We would have healthier working conditions for the workers. We would have more local food. The only people who would suffer a loss would be the fossil fuel companies. Geoengineering is the idea that, well, humans messed it up, so if we just mess it up in a different way, we can fix it. Humans have never been able to do a big project without unintended consequences, often catastrophic. In the 1960s, the Russians built a series of, or the Soviet Union built a series of dams across Egypt as a goodwill gesture to stop the flooding that happened on the Nile every year. It was successful. It stopped the flooding, but that also cut off farmers from their fertilizer every year, and it created a huge breeding ground for schistosomiasis, which is a parasite that lives in snails for part of its life, and then for part of their life, they burrow into your eyeballs and make you blind. So they got a dam. They flooded a bunch of archaeological sites. They stopped the new fertilizer, the new soil coming down every year, and they introduced an ideal habitat for this parasite. The same thing is true of almost all of the large-scale projects that humans have carried out. So some of the ideas that they're talking about, adding chemicals to jet fuel so that the clouds never go away and the sky is more reflective. Or, swear to God, giant space umbrellas or reflectors. Other ideas that are being proposed. Other ideas, sucking the carbon dioxide out of the atmosphere, making it into a liquid, and then pumping it in the ground and praying it doesn't belch out ever. All of the CO2, it's called carbon capture or carbon sequestration, carbon capture and storage. They have built some small units that cost millions of dollars and were able to capture the carbon from one or two cars. So not a cost-effective solution. Switching to renewables is a far cheaper, far easier, far better solution than all of these geoengineering solutions that are untested, unproven, and could be frankly catastrophic and cause hundreds of millions of deaths. Like putting aerosols into the atmosphere. What if that disrupts the Asian monsoon and causes the Asian monsoon to collapse? And so the rice crops of India and China are responsible for feeding half the world. What if that doesn't happen? What do you do then? So geoengineering is very risky. It's very scary. And one of the concerns is that rogue actors, either a country or a group of people, would just start doing this. Like if India was to decide, hey, we didn't burn the fossil fuel, the US did, but it's causing hundreds or millions of people to die from heat waves in India. But if we put a little sulfur dioxide into the atmosphere, maybe it'll fix it. And so maybe one country would decide, we don't care. It's hurting our people, and it's our right to protect our people, so we're going to do what we need to do. And we'll start putting aerosols into the atmosphere or start sending reflectors into orbit or trying to whatever. That could have potentially globally catastrophic effects. What can you do? Not a lot. Not a lot. I used to have a carbon footprint quiz as part of this unit in which you'd go and you'd say like, well, this is how much meat I eat and this is the mileage my car gets and this is how I heat my house. And it would say, oh, to live like you, if everybody on the planet wanted to live like you, we would need 3 or 4 or 5 Earths. But I found out that the carbon footprint quiz was created by British Petroleum to make us feel guilty, like it's our fault. It's not my fault. It's the fault of the fossil fuel industries and Congress. There are systemic factors that I, as an individual, can do nothing about. But they want to put the blame on us because there's nothing we can do. And so by making us feel bad, they're hoping we won't put pressure on our politicians to say, no, we want tougher emission standards. We want more subsidies for renewables. Every year the planet gives $6 trillion in subsidies to the fossil fuel industries. The most profitable, the biggest industries on the planet get $6 trillion of tax benefits from taxpayers. So the poorest people on the planet are paying the richest people on the planet to destroy the planet even faster. If we just put that money into renewables, overnight, we could radically transform everything. And then just a bunch of other last thoughts. Insurance in California, and in fact, insurance across the U.S., homeowners insurance is being changed by climate change. Insurance companies across California are pulling out. They're not writing new properties in fire-prone areas, which is pretty much any place in the state that has trees. And on the East Coast, they're not writing policies in places with hurricanes because they wouldn't be able to charge enough money to make a profit because they're going to have to pay out for catastrophic hurricane losses. So it's a big deal for hurricanes. It's going to be a big deal for forest fires. Here's just a bunch of links to various things talking about flooding. Here's hydroclimatic whiplash. Here's Florida and sea level rise and insurance. More sea level rise and insurance. Dark carbon on Greenland's ice. I don't know. You might be interested. Check them out if you've got a few minutes. More videos, tipping points. Another video on different tipping points. Video on flooding in South Florida. 3 degrees of global warming. I think you have to watch this and answer quiz questions. This video is about the Milankovitch cycles, about how tilt and axial precession and orbital ellipticality, how those three things combine to create these climate cycles. And they include this woolly rhinoceros. More coastal flooding, what that's going to do to New York and Manhattan, like the 9/11 memorial will be underwater shortly. I don't think people are thinking about that. And the end of the chapter. That's it for chapter 7. I hope you enjoy the chapter on climate change. I hope you have a great week. If you have any questions, please let me know.